The last of 4 major topics that need to be reviewed and conquered before accessing calculus is exponential and logarithmic functions. In the review I've been leading, this is the 4th out of 4 topics. The other 3 topics were linear equations and their graphs, functions, inverses, and now finally exponential and logarithmic functions. This section we're going to take a little slower because for my own students this is where we stopped and this is where we are continuing on from. We're going to start by talking about what makes exponential functions different from functions with exponents that we've seen before. We've seen functions such as x squared, where the unknown or the input is in the base, and then the exponent itself is a number. Exponentials are the other way around. That's when the base is a number, and the unknown or the input, or x, is in the exponent. Let's take a look at what this might look like because we've actually already seen exponential functions for rational values of x or for rational exponents. Here we'll use the base of 2. We know 2 raised to the 0 is 1, 2 raised to the 2 is 4, 2 raised to the negative 1 is 1/2, and 2 raised to the 1/2 is root 2. These are all rational exponents because if you notice, the exponent itself is a rational number of some form. The properties of exponents are as follows. Some base raised to 0 is always 1. And then we have some exponent properties when you have a base raised to a times a base raised to y. We actually add the exponents. For an exponent raised to another exponent, we multiply them. For a base raised to x over a base raised to y, we subtract the exponents. And furthermore, we have to remember that we do distribute an exponent to pieces within parentheses. For these basic examples, make sure you can match the answer to the property that was used to get to the answer. Now we're going to sketch some example graphs of exponentials. I'm going to use an input-output table. My input is going to be represented by x, and I'm going to output a couple different example functions, 2 to the x, 2 to the minus x, and 3 to the x. So here's a list of all the inputs that are going in for x, and so for example for 2 to the x, when I put -3 in, it outputs 1/8. When I put -2 in, it outputs 1/4, and so on and so forth. And so I'm just filling in the table in that manner. If you would like to, you can pause here and observe the patterns in the numbers. When we graph these on a single set of axes, we're going to note that for many of these first values, they're going to be so close to the axis that I kind of can't physically show them in the real world. So, I'm just doing the dots as close to the axis as I can. For all 3 of the graphs, we should note some interesting characteristics. One is that they all pass through 0, 1. The other is an interesting comparison between the purple graph and the blue graph, which is 2 to the x or 2 to the minus x. Look at this mirror image happening over the y-axis. And the other interesting relationship is between 2 to the x and 3 to the x. Same exponent but different bases. Notice that the green graph dives a little lower, but then comes up a little quicker. In general, these graphs look like the following. When you have some y equals a to the x, it's going to rise, passing through 0, 1. And when you have some graph y equals a to the negative x, it's going to descend or decay, also passing through 0, 1. Here are the properties as long as the base a is greater than 1. 1. The domain of a to the x and a to the minus x are both from negative infinity to infinity. The range of a to the x and a to the minus x are both 0 to infinity. The y-intercept of both a to the x and a to the minus x is at 0, 1. And finally, both of the functions, f of x and g of x, are 1 to 1. Let's talk about the number e. E does have an approximate exact value. It's an irrational number. We're not going to dive very deeply into where it came from, but I am going to show you how we do find it by graphing. So I am going to graph the following function, 1 plus x raised to 1 over x. So I'm going to do that with an input-output table. I'm going to have some values of x that are going to go into the function, and where they output on the y-axis is where I'll be graphing them. And so it's going to look like this with a little whole and unallowed value at a particular place. I'm not allowed to input 0 into the function because then my exponent will be 1 over 0, which is not allowed. But I can get really, really close to see what's going on in the graph near that place. So here I'm just graphing a bunch of numbers on either side of 0 that are really, really close. And you're going to notice in the table that as it gets really close to 0, it gets really close to a particular number, which is the number e. And the actual definition of e is the limit as x is approaching 0 of this function is in fact the value e. Now we're going to graph the function e to the x. I'm going to input some values and it's going to output in the function e to x. And when I graph this, it's going to look very familiar. It is going to be an exponential curve. We'll also note that it passes through 0, 1. E to the x and its various forms is a very important graph in mathematics. So let's talk about undoing that graph. Let's talk about the inverse, the natural logarithmic function. When we have a logarithm whose base is e, we have a special way to write that to denote that this is base e. We call it the natural log, and we instead write it as ln of x instead of log of x. Log form and exponential form can go back and forth. We can rewrite one as the other. Let's do some important examples for e. So ln of 1 is 0. In other words, e to the 0 is 1. ln of e is 1. In other words, e to the 1 is e. And ln of e to the negative 1 is negative 1. In other words, e to the negative 1 is 1 over e. If you remember in my own class, I like to show the scorpion tail method for going back and forth. Since this natural log is a base of e, if we scorpion tail, e to the 0 is 1. And that's what we have written over there. Let's practice again. This base is actually e, so when we scorpion tail, we would rewrite it as e to the 1 equals e, which is what we have written over there. In all cases, when you do the scorpion tail method, you're following the scorpion tail for the order in which the numbers are supposed to occur in the other form. Let's look at the properties of the natural logarithmic function. First of all, the domain of natural log is 0 to infinity. The range of the natural log is from negative infinity to infinity. The x-intercept of the natural log is at 1, 0. And finally, these functions are 1 to 1. And in fact, these properties should look familiar to what we wrote before, but a little different. In fact, they should be flopped, because this is the inverse. And because they are inverses of each other, we can conclude the natural log of e raised to the x is x, and e raised to the natural log of x is x. I'm going to re-show my scorpion tail method for going back and forth between log form and exponential form. It's just a fun way to remind there's really no particular reason it's called scorpion tail, besides it's kind of cute and you will remember it that way. So when I have some log base a of x equals b, I can rewrite it by going a to the b equals x. We call the common base, when we don't see a base at all, is going to be 10. So that means when I'm just looking at log of 4, it is implied that that base is 10. The natural log of x is b, and it's always implied that that base is e, so this will be e to the b equals x is the other form. There is no other way to use this base, so ln of 10 is always going to be ln base e of 10. You'd never ever see ln base 2 of 10. It doesn't make sense. ln means the base is e. There are 3 major properties. The first is ln of xy equals ln of x plus ln of y. ln of x over y equals ln of x minus ln of y, and ln of x to the z equals z log x. We wrote these down before using the log form. Here's the first one in log form. It's the same. Remember, ln is just a special log, so you can rewrite them one way or the other. And these are the 3 major properties. We're going to practice with them now by doing some expansions of logs. The property that we see here is the division is going to become subtraction, so this will be ln of 10 minus ln of 9. The property that we see here is that sneakily this is actually 3x plus 2 raised to the 1/2. And so this is an exponent rule. It's going to come out front. In this example, we're going to see that we have 6x over 5, so that's going to expand by subtraction. But there's a further expansion because 6x is actually 6 times x, so that can expand one step further. We're now going to do a final challenge, and so this is going to be a quite large argument inside our natural log. And we're just going to pick it apart. First, we have a numerator and denominator. So the first thing is I'm going to do the ln of the numerator minus the ln of the denominator. I'm then going to color code them so you can kind of see them as they are separated. And then we're just going to deal with each of them separately. For example, look at the purple piece. Now just looking at purple, can you see that we now have an exponent rule? That 2 is going to come out front to further expand it. And now that piece is done. Furthermore, can you see that this is the natural log of x times the natural log of the cube root of that stuff? From here, I'm going to color coordinate it again. So I'm going to show you this purple piece. Looks like it's actually fully expanded. Next, I've got a darker blue piece that is fully expanded and another blue piece that needs one further expansion. We saw this trick earlier in an example. That cube root is actually that whole thing raised to the 1/3. So I expand it by pulling the 1/3 out front. And now we have fully expanded this challenge problem. You can pause on any step to take a look at it deeper if you need to. And of course, the last piece of all of this is using the knowledge to actually solve equations. Let's solve. Here's an equation. And remember, when we solve, we're always trying to find out what x is. But how do I solve for x? How do I undo things to get this x out of where it is, which is in this exponent? Well, I use inverses. First, I need to get it out of the exponent of e, so I'm going to take the natural log of both sides because that's the inverse of e. I'm going to do this part out explicitly. Look at that exponent rule. That x plus 1 comes out front, and ln of e is just 1. Usually when we do these in class, we skip right to the ln and e canceling each other out and pulling that exponent down. But really, it's been this exponent rule the whole time. Either way, you're going to get natural log of 7 equals x plus 1 for your next step, and then it's as easy as moving the 1 to the other side of the equation. If you were asked to put this in a calculator, that's fairly simple. ln of 7 is a number, and you'll get an approximate answer. If you do this for practice, you should get approximately 0.946. We're going to do one more example. So here we're going to have an equation, and again, we're solving for x. Right now, x is inside an argument of ln. How do I get it out? Well, I need the inverse of ln, which is e. So I'm raising both sides of the equation into e. And on this left-hand side, when I do that, the e and the natural log are going to cancel each other away and leave 2x minus 3. From here, it really is a simple algebraic equation that we have done many times before. First, we're going to do the additive inverse. We're going to add 3 to both sides because it is in a separate term than the one that x is in. And finally, we're going to do the multiplicative inverse, and we're going to divide 2 away on both sides. Here we'll have an exact answer. Remember that e is a number, so e to the 5 is a number. Or you can take it a step further. You might be asked in a question to use your calculator to find an approximate answer. If you do practice this, you will get approximately 75.707. You'll have an exact answer here highlighted and an approximate answer highlighted. So ends the final topic.